No need to pre-pad the recording with that, so I restarted recording. So the other data structure we learned about was the queue, right? I'll go ahead and go into JShell for you guys for this one rather than trying this thing. All right. JShell. Fortune decided to be cynical today. All right. So JShell. So the first thing is that queues in Java, native queues in Java, not like any queue that I wrote, but the way a queue works in Java. Let's make a queue of integers. Queue is equal to a new. It's an interface, so I'm going to implement it using the linked list data structure. So, and as you can see, and the reason for doing that is it allows me to just, if I try to do like queue.add, it'll prevent me from doing that. That's okay. Oh, no, won't. Never mind. Queue.add. Make me a liar, I guess. So queue.add index 1. Okay, yeah, it makes me a liar there. Okay. So queues, essentially, you can, the way a queue works, again, is that they have only 4 methods that we really care about, and any other methods they have are duplicates of the ones they already have. So there's 4 methods we care about. First, so queue dot, now when I'm talking about a queue, I mean exactly what I say. I'm talking about essentially a line, right? A line of people in the queue, right? And we enter the line by entering the back of the line. And we do that by offering something to the queue, so I'm going to offer 5 into the queue. And if we print out our queue, our line is 0 and then 5. And then if I put in queue.offer 1, we've got 0, 5, and 1, right? Let me go ahead and increase the text size for you guys. Okay. So you offer things to a queue rather than pushing things on, as opposed to pushing things onto them, right? You offer them, you get into the back of the line. Just like if you're at the grocery store, you get into the back of the line. Now the person who gets served next is the front of the line, which is also, and another way of looking at that is that the item that gets processed next is the one that has been waiting the longest so far, right? The guy at the front, he's been waiting the longest. The guys who are in the back of the line, they haven't been waiting as long, right? Because if they had been waiting longer, they would have been at the front of the line. So queue.pull to pull them, to get them off. So that should return 0. And if I pull again, it will get 5. And now our queue is just 1, right? We've removed the first person in the line, then 5, and then 1. So that's the only way you can add to the front. There was an add method as well, but it also added, it was just a duplicate of pull. It's just something different than, but yes, there's nothing. Yes, was that a question or no? Okay. There's really only 4 methods. Let's pull again. Now it's an empty queue, so there's also an empty method. I might write it as, okay, it's an isEmpty. Yes, an isEmpty method. Awesome, yes.
So, you mentioned that the queue is actually the interface.
Yes.
So, does that mean that when we do a linked list as a list, is it going to also have these because we're using the class linked list?
Excellent question.
In which case, does it really matter how we declare it on the left side of the assignment?
It does. It matters, it matters very short. So I'm just going to do the L.offer 1. So yeah, you totally could do that, right? You could totally use a linked list and use the queue methods in there, right? Very good observation there. Now, does it matter? So the answer is that when we go back to using our queue, whereas I could totally use L.add index 0 and 1, right? And we print out our list, right? Index 0, 5, right? And I can put something right there. By using the queue interface, it prevents me from directly accessing all the other methods. The only thing I can use, all Java knows is that the queue is some class that implements the queue. It doesn't know which one. It doesn't keep track of which one you use to implement it, because that could have changed if you made a new queue. So we could do queue dot So if I try doing q dot add 0, well, let's see. Do I have anything in the queue even? No. Q dot offer 1, q dot offer 2, q dot offer 3, q dot, and now if I try to do q dot add 0, comma 5, this prevents me from adding it into the beginning of the queue. This prevents me from cutting in line. Okay, which is, and that's useful, right? Basically, you're saying you can only use this thing as a queue, right? Now, of course, I could do some. There's ways around that, like with casting, but that's generally considered to be bad practice, right? You shouldn't cast because you should have what you intend it to be. So as a queue, we're just limiting ourselves to 4 methods. The 4th method of being peak, right? Just like the so the 2 of them ones are the same as the stack, and 2 of them are the same as and 2 of them are just different names, but they do the same thing. Adding to the end and removing from the front. Okay, so these are both constant time operations. Now, as opposed to a stack, stack is LIFO, last in, first out. Stack is FIFO, first in, first out. The first person in line is the first person to be served, right? And it works very intuitively. So when do we use the queue? Well, they're a bit more intuitive as to how we use them. We use them when we want to go through things in a specific order. We use them when we have to have a list of things waiting to be processed, whether it being print jobs or jobs that are on your computer's task manager, or items that need to be processed. Anything there, basically things have to wait. A network buffer is an example of a queue, right? Things are waiting to be sent out by a router or waiting to be processed by a router. That's going to be kept in the queue. So these things are pretty intuitive as to when you would want to use them, right? Later in the semester, but we'll see them more when we get into breadth first search, and when we get into which is near the end of the semester in chapter 10, when we go through a level-based iteration, a level-based order of a tree, which is in chapter 7, and again in chapter 7 when we write what's called a priority queue, which is a much more realistic queue, where a lot of times there's instances where we have a queue where we want people to be able to cut in line, like in a hospital situation, right? They have the waiting room. You want the person who's possibly needs to be treated for a heart attack to be seen before the person with the broken arm, right? That's what we call priority queue, where people cut in line. It's a queue where people are waiting, but we allow people to cut in line based on how severe something is, right? For instance, some jobs that your computer needs to handle are more important than others, so we want those to be able to cut in line. So we'll see those back in chapters, no, not 7, 6. All right, any questions about a queue? They should be fairly straightforward. You don't need to understand them for the most recent homework. All right, yeah, you're not really going to need them from the homework because any kind of assignment I come up with is like the most ridiculous. They're dumb, really. The assignments I could come up with are dumb, whereas the maze is actually interesting, right? Which is why I'm doing the maze and focusing on depth first search there. The other thing I want to go over is quit / exit. Yay, okay. The other thing I want to go over is here in Genie. So from the session I had last night, I saw that people were having trouble getting started on the solve maze. The most common question is like, so how do I actually move in the maze, right? So I have this. So the first thing is that this PDF that I made, teaching destruct assignments. Yep, maze. Right. This PDF is this algorithm over here. If this algorithm with some moderation will give you the answer with some minor moderation. Modification, not moderation. So the first thing I do, right, is my condition is while the stack is not done, while maze exploration is not done and the stack isn't empty. You'll have to figure out how you can tell exploration is done. Great typo there. and the stack isn't empty. That should easy to figure out. This one's a bit harder. So the first thing you want to do is peek to get your current stack. Sorry, just peek the stack to get your current cell, the cell where I currently am. And then you make all your decisions locally based on that cell's information. So first off, if we can go north and we haven't visited there yet. Okay, so first off, how do I know if I can go north? Well, I know if I can go north if there is no wall there, right? And in my cell, I keep track of whether or not there's a wall. So I could write something like, if not current, so if north wall, right? And this says if there is not a north wall where I currently am, if there's not a north wall, okay, that means I could go north, right? The other thing is like, how do I actually get north, right? What is if I wanted to refer to the coordinates for the north one, because the other part of it is, and if I haven't visited there yet. So I've got this visited, I've got this visited function I wrote, visited, which takes in a row and a column. Okay. Now, so the way this one's going to work is that I can get the square to the north pretty easily. This will come later, getting a square to the north pretty easily. But if I want to check if the guy to the north has been visited or not, right? I got to give it a row column. So I would go something like visited. And then I can find out from my current cell what row I'm in by going .row. And what column I'm in. So that's where I am. Now, one common thing I saw was people were doing plus plus and minus minus over here. Do not do that under any circumstances. You will that will ensure that your program will not work, because that means modifying that will modify this value. It will change this value, and you don't want to do that. Okay. Instead, use plus 1 minus 1. Now, another big thing to know is that most of you that some people were working in the wrong coordinate plane. So let me explain with my mouse cursor. Most of the time, you think of it like this. Like this direction up is positive y, right? And so that this corner over here at the bottom of my screen, that would be 0, 0. And that's not the way it works in computers. The way it works with computers is that this square, this pixel over here is 0, 0. This one in the top left corner, this is 0, 0. Just like how if we're looking at a 2D array, this would be row 0, column 0. This would be row 1, column 0, row 2, column 0, row 3, column 0, and so on and so forth, right? Right? So let me go ahead and illustrate that a bit more forcefully. Right? This square would be 0. So if I were to make a grid, it would look like this. 0, 0, 0, row 0, column 1, row 0, column 2, 1, 1, 1, 0, and 2, 0, 1, 1, 1, 2, 2, 1, 2, 2, right? So if I wanted to go north, I would subtract 1 from my current column. So subtracting gets you north, and adding 1 gets you south. East and west work exactly the way you would think it would. Okay? And because you're dealing with row columns, they're also kind of swapped around from x and y coordinates, so keep that in mind. All right? So just as a little bit of questionnaire, just to make sure you got that. So Maze keeps track of all the cells. If you need to push something on, if you want to move somewhere, you're gonna go ask Maze for the cell that you want to go to and push that onto the stack. That way, next time around in this while loop, when you peek at the stack, it will be the one you just moved to. Okay. So this gives me current row and current column. This gives me the current cell I'm at. So if I wanted to get the cell to the north of me, what would I want to do? column minus 1 would be the one in a different direction, because column, believe it or not, is the left-right direction. It takes a bit getting used to. When you're modifying the column, right, that modifies what column you're in, which means you're going to the left or to the right. Right? It's flipped around. It's weird. So if I wanted to go north, I want to modify the row. How would I modify it? Row minus 1. Okay? So this is to the north. So this is what? South. Okay? And this one would be, yeah, it would be east. Okay? And now if I were to do this, you can't, and now in our maze, you can't go diagonal, but let's assume you could. That would be northeast. Northeast. Right? So, anyway, that's the little primer on directions there, which I always forget may be left out if you, you might not necessarily intuit, right? Because, if you don't intuit that graphics are going to work the same way as arrays do, right? And the reason we like this is because over here, this pixel 0, 0 is row 0, column 0, right? That's why we like it. And so it matches our visual representation of arrays. All right, so that's it. I'm going to go ahead and, so there's 50 minutes left. I feel like I've dawdled enough on, and so now you guys should be able to, so I should be able to help you guys out. A number of people in the morning lecture did manage to finish the assignment, right? And they pretty much just started, today. So it's not a particularly short assignment. You should have plenty of time to work on the extra credit, okay? So I'll be happy to help you out there.